Hello boys and girls. So this video will be a kind of more fancy Hello World program for Idris. We're going to implement one Idris function and thereby showcase some features. And it will also basically be Haskell code involved. You have to just to change a few characters maybe, and then most of the code will also compile on Haskell, but of course on Idris you have the dependently typed features. The video also ties to the videos I did 2 days ago, where I implemented various ways of computing the power operations on power operation on collections. In particular, in Python I did the power operation on lists, and this itself was motivated by the video talking about the set theoretical universe of finite sets, and then going beyond the power operation, actually generating all combinations of some symbols and objects. But so nevertheless, I will come back to those things as well, but let's just jump into the coding part of this video. I will recall what we had at the end of the Python video. This was one of the implementations. I think I had 3 or 4 implementations, and the last one is closest to a sort of functional implementation that can be translated quite literally. Let me first run this. So I go Python, the file is called power.py, and here I get the list of all sublists of this list. So here we have a list of 4 elements, 0, 1, 2, 3, hello, 0, 1, 2, hello. And here we get these 16 elements that are exactly the sublists of this list. I print the list and then also its length. And of course, if I were to, remove these, then we expect to get a list of 4 elements, because 2 to the power of 2 is 4, and so on and so forth. Okay, that works. Let me quickly recall how the algorithm works here. So we saw a few algorithms. They have a lot of things in common, and this is the one where this recursion comes in. So let's say we have this list of 8 elements, which is the power set of, or list of power list, if you want to say, of this one. So 3 element. If you take the power operation of that, I get to this 8 element list, and we can see this recursive structure there. Namely, let's take any element out of it. It makes sense to take the first element for implementation's sake, and then we see, well, okay, these are these elements that don't contain the 0, and the other 4 elements. So it splits in 2, and the other 4 elements, they have also the same subsets in it, except there's the power set added. So this set is exactly the empty set plus the 0 added. This set is exactly this set, but with 0 added, and so on and so forth, right? So to compute the power set, we can compute the power set of one of the subsets, and then just add to make another copy of the power set, add all the elements back, and then we have the full subset. And so this is where the doubling comes in. That's why it's the power of 2, you could argue. And so implemented in this Python function that I call this power.py. Well, if the set, I call this v's for values, is the empty set, then basically by convention the power set is the set containing just the empty set. So you can say that this is the only subset of the empty set is the set itself, and so that makes sense, and it also works with the arithmetic. And otherwise, split the set in 2, so it makes sense to take the first element, because we always know at this point that there will be a first element, call it x, call the rest of the elements, how many there may be, xs, and then do this recursive call where you compute the power set of this smaller set, the one which has 1 element removed. And then you return this set plus this set with the x added back, and for this sake I introduced this function here, which depends on x, that we just defined, that prepends this x. And this is exactly what we were going to implement now. So first we write the kind of Haskell version, if you will, with a few tweaks, but removing some characters and changing some letters will give you compilable Haskell code. So for this we go into Idris, and I have this here typed power. It's the name of the file. Let's start it. Okay, so what we do, well, we define one function that's called power and then L, because I'm first going to implement it with lists in the type. So this is naturally going to be from lists of some type to lists of some type, right? And so we have a type parameter here, and in this Idris file I can go with this notation here. Yeah, what is it going to be? Well, same as before. On this initial case of the empty list, I return the list containing the empty list, and otherwise we're going to do some pattern matching on the input argument. So we're going to split it in X and XS, just with, like we did more manually with Python. And this is going to be, well, we were going to return pxs plus map and then prepend, and the prepend is just this expression in Haskell and Idris on this. So you should be familiar with this addition of the power set and the map on power set. This is exactly this here. But of course we have to still state what is actually the pxs. Well, pxs is this recursive call, and that's it. Plus plus. So let me reload this. Checks out, and I can use it. Power L of 0, 1, 2. It tells me, well, this ought to be this 8-element list of list integer. Okay, and of course, you know, I can tweak this. Let's do some tests. This is a heterogeneous list in this case, so if I call it on hello world, then I get the power list basically of the hello world as a list, but I shall not mix them, yeah, as expected. And I can also, I mean, I can run it on the empty list, but then there are many instances. So one way I get around this would be to say, well, I want it of net, and then I get this empty list of, you know, known natural numbers. Okay, so far so good. Now let's rewrite this actually to one that works on vectors in Idris. So the vector also knows about the sizes. We have to import the library here. So import data.vect, and we just have to make a few tweaks really. So not just do we abstract over A, but we're also going to abstract over the size, the input size. And this is going to be called n, and it's going to be a natural. And so here, instead of list, we have vect of dependent on this n. And so we're going to get a bigger vector out of it. And we know that this is going to be a power of 2, or at least we demand that this is going to be, and the compiler will actually make sure that this is actually the case. So it will not compile if the math would be any different. So there's an operation actually called power that actually just takes the arithmetic power. So I don't, I can really use the name power. I don't want to, because there's also the internal standard library Idris power. So name clash there. But we know that this is the result vector will going to be 2 to the power of n, right? Because of this doubling effect. And so this will be enforced and noted by the compiler. So what do we have to make for changes here? Well, if I try to just stick with that, then he will have a problem. Namely, since the implementation of the plus operation internally, that, you know, very proof theoretical approach, he doesn't actually recognize by itself that some number plus 0 is just a number. And this has to do with the fact that if you look at the implementation, you have to make a choice between in the recursion scheme of plus. And so this also, you know, appears when you look at the recursive definition of the plus operation. So for example, here is the Peano axioms of the natural numbers, and tells us that a plus 0 is ought to be a, and then with the successor function how to actually compute the addition. And this is different. Saying that a plus 0 is a is different a priori from saying that 0 plus a is a, right? There's in the recursive scheme a choice made left and right, and something similar happens here. You can actually, of course, people coming from let's say a less mathematical language are going to be typically surprised by this kind of intricacies, and so you'll find enough Reddit questions and elaborations and also in the tutorials on this particular issue. So what do we have to do? Well, we have to tell the Idris that we know about how to resolve that, and indeed this is easily resolvable because there is a constant in the library called plus 0 right neutral. That is basically the proof that this works. And so we add here, please rewrite plus 0. We're going to use the right neutral for this expression power 2n in this expression, and for clarity's sake I'm going to give this another name, n prime, and also going to say here that n is used on this n prime, so this is not the 0. This is not 2 to the power of 0. In the 0 case, we have here covered, so this is a successor. And if I'm not mistaken, that should be it to resolve this small thing. And indeed, so let's try it out on what we had before. Let's say here, but now with v, and we get a vector of list 8. So you see here the difference with Idris is that now we have actually the code and the type depend on this term of net, not just abstracting over type, but also over natural number. And we can encode, you know, all kinds of information. We can be stricter and stricter. We can load more and more information into this type, and then see if the compiler agrees, and otherwise we are probably wrong and the compiler is right. So that was it for today. I stick in under 15 minutes. Very proud of myself. I hope you like that, and I'm likely to do more Idris in the future, so I look forward to that. Take care.